This lecture is about normal proof. A normal proof is basically a proof without detours in it. Proof without detours in it. So previously, we have learned that for any proof of A true with a detour in it, so this is a detour, we can apply local reduction to get rid of this detour. And by extension, it turns out that for every proof of this truth judgment A true, there exists a sequence of local reductions that eventually lead to a proof of the same judgment with no detour in it. So we start with a proof of A true with many detours perhaps, and then we can apply a sequence of local reductions to produce another proof of the same judgment but without detour. And this is called normal proof. And we can show that the size of this normal proof is minimal with respect to some particular metric, although syntactically the size of this proof can be much larger than this one. So let's take a look at the pattern of normal proofs, what it looks like. So normal proof has no detour in it. So in order to prove, let's just say C true, we would apply introduction rules and keep moving upward. And while we apply this introduction rule, so these guys are all introduction rules. When we apply these introduction rules, we perhaps introduce many hypotheses. So these are hypotheses that we introduce when we apply these introduction rules. And starting from these hypotheses, we apply elimination rules. So we keep applying elimination rules. So when we decided to apply introduction rules, we try to build a derivation tree for the goal judgment. And when we apply these elimination rules, we try to exploit an existing judgment. So we keep moving downward here, and we keep moving upward here. And in the middle, this application of elimination rule meets with the application of introduction rule. So we can imagine that the construction of a proof for this judgment C true without introducing any detour would look like an hourglass, where the lower half consists of introduction rules, and the upper half consists of applications of elimination rules, starting with these hypotheses. So we'd like to focus on the direction indicated by these arrows. So these down arrows, imply that we'd like to apply elimination rules to exploit existing judgments to move downward. And these introduction rules imply that we'd like to apply introduction rules to build a proof that has not been completed yet. So a normal proof usually looks like this hourglass. At the bottom, we have the goal judgment, and we keep applying introduction rules and move upward. So these are applications of introduction rules. And In the upper half, we have hypothesis, and then we move downward by applying elimination rules. And in the middle, this down arrow or the elimination rule meets with this up arrow or this introduction rule. So the shape of this normal proof complies with the intuitive way of constructing a proof. Let's see an example. Let's try to build a proof A conjunction B implies B conjunction A true without any detour in it. So we'd like to build a normal proof with no detour. In order to build a normal proof, we will first apply implication introduction rule. So we move upward, just like here. So we move upward by introducing a new hypothesis, A conjunction B true. Let's say this is X, this is X. And now we want to build B conjunction A true. So we want to build here instead of exploit. This hypothesis will be exploited later because we assume that there is a proof of this judgment. But for this goal judgment, we have to build new proof. So we will keep moving upward here, whereas we will move downward by applying elimination rule later. And in order to build a proof of B conjunction A true, we apply again introduction rule. So conjunction introduction rule, and then we keep moving upward. And now we have two goals, B true and A true. Still, we have to move upward because we have to build a proof of B true and a proof of A true. So we want to move upward. Now it's time to exploit the proof of an existing judgment. In this case, it's going to be this hypothesis. So let's apply conjunction elimination rule to exploit an existing judgment. So we move downward. And by applying conjunction elimination right rule, we have B true. And similarly, we replicated this hypothesis and then apply conjunction elimination left rule. And then we obtain A true. So we want to exploit this judgment to be true in order to build the proof of B true. So here, this down arrow meets with this up arrow. And similarly here, this down arrow meets with this up arrow. So we can imagine that there is an hourglass that looks like this. In the upper half, we apply down arrow or elimination rules, starting with these hypotheses. And in the lower half, we keep applying introduction rules to move upward. So that's the basic idea behind constructing normal proofs. And before we formalize this notion, let's inspect an important property of normal proofs. The normal proofs, property of normal proofs. So it turns out that A true is provable if and only if there is a normal proof of A true. So this direction can be interpreted as soundness of normal proof, which simply says that if there's a normal proof of A true, then we have a proof of A true. That is, a normal proof is a valid proof or just normal proof is a particular case of an ordinary proof. The other direction is called completeness, which says that if there is a proof of a judgment a true, then there must be a normal proof of it. And it has two important implications. The first is, if you'd like to build a proof of A true, or if you'd like to show that A is true, then according to this completeness, it suffices to show that there is normal proof of it. So to show that A is true, then try to build a normal proof of it. That's enough. And the other implication is, now you'd like to show that A true is never the case. So in other words, you'd like to refute this time. Instead of proving, you'd like to refute A true. And according to this completeness property, if this is false, so if this is not the case, then there should not be normal proof either, because this is if and only if. So if A true is never provable, then your attempt to build a normal proof of A true, this should fail as well. This should fail. So as a result, in order to refute A true, try to build a normal proof of A true, like moving upward by applying introduction rule, and then moving downward, starting from these hypotheses, and show that your attempt eventually gets stuck. If you can show that this attempt eventually gets stuck, then you have shown that you can never build a normal proof. And by this soundness and completeness property, you can conclude that this is not provable. So normal proof is such a powerful tool for investigating the meta properties of a logic. And the ultimate goal in studying this normal proof is we'd like to show that global soundness of the logic system that we have formulated, that is, bottom true is not provable. And later, we will actually prove that bottom true is not provable, and we will use this property, the completeness of normal proofs. So this is a mild introduction to the concept of a normal proof. To summarize, normal proof is proof with no detour. And if you construct a normal proof of a judgment, the proof usually looks like this hourglass, where the lower half is comprised of applications of introduction rules moving upward, and the upper half is comprised of applications of elimination rules starting with these hypotheses. So we move downward. And in the middle, this elimination rule meets with this introduction rule. So that's the typical way of constructing normal proof. Now, let's formalize all these ideas. In order to formalize this idea behind the normal proof, we introduce two new judgments. The first is what's called neutral judgment. And we write a down arrow. And the other is normal judgment. And we write a up arrow. And normal judgment is proven with what's called a neutral judgment can be proven with neutral proof, and normal judgment can be proven with normal proof. So this neutral judgment is a notion that is an auxiliary notion that we introduce to formalize this notion of normal judgment. And this neutral proof is basically what appears in the upper half of this triangle, this hourglass. So it is either hypothesis. Here we have hypothesis. So this is basically an example of a neutral judgment. Or elimination rule applied to an existing neutral proofs. Existing neutral proofs. So basically we introduce this neutral judgment for all those judgments that appear in the upper half of this hourglass. So let's go back to the example. So its hypothesis, perhaps it's going to be down arrow, neutral judgment, and application of elimination rule to an existing neutral proof is also down arrow. And the definition of normal proof is basically what we see in the lower half of this triangle, hourglass. So first, this one that lies at the intersection of this upper half and lower half, this is counted as normal proof. And right above here, we have a down arrow or neutral. And here we will have a up arrow. So to account for this particular case, we define neutral proof as a normal proof. Or it's an introduction rule applied to an existing normal proof. So this normal proof, or this A up arrow, is basically what appears in the lower half. So there is a good reason why we choose this down arrow and up arrow. Down arrow for neutral judgment and up arrow for normal judgment, because the direction of this arrow indicates the direction in which we construct the construction of normal proof proceeds. What that means is that in order to build a derivation tree for this A up arrow, you would keep applying introduction rule and move upward. And in the course of applying these introduction rules, you would introduce hypotheses. And these hypotheses are ready to move downward. So you can annotate these hypotheses with this down arrow. So here we apply introduction rules. And for starting from these hypotheses, you apply elimination rules. So you move downward. So every time you apply this elimination rule, you create another down arrow. So this direction, this arrow is the direction indicates basically the direction in which the construction of this proof proceeds. In the upper half, we move downward, and in the bottom half, we move upward. And the direction is indicated by this arrow. So we would see a bunch of normal judgment in the lower half, and with a bunch of neutral judgment in the upper half. And in the middle, we will see this A down arrow meets with this A up arrow. So that's the idea behind these two new forms of judgment, neutral judgment and normal judgment. And this is the formal definition. Neutral proof is either this hypothesis or elimination rule applied to an existing neutral proof. And normal proof is either neutral proof. So this is a neutral proof because it is annotated with this down arrow. And we can take this neutral proof as a normal proof. So we make a silent conversion here. So neutral proof is counted as a normal proof, and an existing normal proof, and we apply introduction rule, and then we obtain another normal proof. So that's the formal definition, the definition of neutral proof and definition of normal proof. And we'd like to remember that neutral proof is all about down arrow, applying elimination rule, or exploit. We already have a proof of we already have an existing proof of a judgment, and we'd like to exploit and move downward. And the keyword for this normal judgment is instead of build. We have yet to build the proof of this judgment, so we'd like to build and move upward. So you want to remember downward means exploit, up arrow means build. Now let's investigate the inference rules for this neutral judgment and normal judgment. First, let's consider this special case. According to the definition of normal proof, a neutral proof is counted as a normal proof. So in the middle of this hourglass, we see this conversion from down arrow to up arrow. So to deal with this case, we have this inference rule, conversion rule. Conversion rule literally converts a down arrow into a up arrow, and we can call this rule down arrow, up arrow. And basically what this rule says is this one, neutral proof can be converted to normal proof, as stated in this definition of normal proof. So now we have this special rule called conversion rule. Now let's analyze the remaining inference rules for neutral and normal judgment. Remember that we are going to build this hourglass shape, and in the middle we have this application of this conversion rule, like a down arrow, a up arrow, and in the lower half we will perhaps have a bunch of a up arrow stuff, and in the upper half we will have a down arrow stuff, and at the end we have hypothesis, a down arrow. So first, let's consider the logical connective implication. Suppose that we'd like to build a proof of truth judgment. A implies B true. Because we would like to build a proof of this judgment, we want to use up arrow. So remember that this keyword, the build, is associated with this up arrow. And in order to construct the proof of A implies B true, we apply implication introduction rule, and then we introduce a hypothesis, A true, and this is waiting to be exploited. So it's going to be annotated with the down arrow. And now we have to build a proof of B true. So I just said build a new proof of this judgment to be true. So therefore, we have to move upward. And if this is labeled X, we have to label it with X. And this is basically implication introduction rule for this normal judgment. So we annotate with up arrow to indicate that we are applying the rule to this normal judgment. So there's nothing surprising here. The direction that the proof of construction proceeds, bottom up, and the way that this hypothesis is used or exploited complies with our intuition that we have had so far. So that's the first inference rule for logical connective implication. And what about the elimination rule? Again, there's nothing surprising in this implication elimination rule. Suppose that we already have a proof of A implies B true. We already have a proof, and then we'd like it to exploit by eliminating it. Because we want to exploit, we want to annotate it with down arrow. Now, how can we exploit an existing proof of this judgment? It's our responsibility to build a proof of A true, because this is not given for free. It's our responsibility to build a proof of this A true. So because we have to build, we have to use up arrow. We are supposed to complete this derivation tree, and it's not given from the outside. Now, suppose that we have finished constructing the derivation tree here. Then we apply implication elimination rule, and by combining these two judgments, we have just found a proof of the true. We have already built proof of this judgment, and this judgment is waiting to be exploited again. So we move downward. So this is implication elimination rule, down arrow. Again, there's no surprise here. Well, in order to use an existing judgment, we have to build, so we have to move upward. And after that, we keep moving downward because this judgment is waiting to be used, waiting to be consumed. So we have finished the discussion on this implication connective. And let's look at the conjunction. In order to build is indicated with this up arrow. In order to build this A conjunction be true, you have to build, so up arrow, and you have to build be true, so it's up arrow. So this is a conjunction introduction rule, up arrow. Now, let's eliminate an existing judgment of A conjunction be true. This time, we'd like to exploit, so it's a down arrow, because we assume that there is an existing proof of this judgment. And then, by applying conjunction elimination left down arrow, we can create a proof of A true. And this one is again waiting to be exploited. So we'd like to exploit this one. So we move downward. And there's a symmetry case, conjunction elimination right down arrow. Now let's the most complicated case, disjunction. What about the introduction rule? We'd like to build a proof of A disjunction be true, and this time we'd like to build. So therefore, we have to move upward. In order to build, you have to either prove A true. So if you choose the left side, then you have to build again. You have to build the proof of A true. So again, you keep moving upward because you have to build. So this is disjunction introduction rule, left rule, up arrow. And the symmetric case is A disjunction B up arrow. This is B up arrow. This is disjunction introduction right up arrow. What about the elimination rule? We start with A disjunction be true. And we already have a proof of this judgment. So we want to exploit this existing judgment. So we move downward. Now we have to consider two cases. First, A is true, and we assume A true. So we exploit, this is a down arrow. And the other case is B down arrow. Now there remains a question. So we have C true here, and we also see through here, and see through here. And the critical question here is, which direction should we use for this see-through? And if we think about this, we can imagine that instead of moving from A disjunction B down arrow all the way to see-through, we can imagine that we are approaching this disjunction elimination rule from both ends. From this end, we are moving downward. And from the other end, we are moving upward. So we can imagine that currently we want to exploit an existing judgment A disjunction be true. But at the same time, we have not finished building a proof of C true. So we'd like to build a proof of this judgment C true. And alternatively, we could say we exploit A disjunction be true, and after that we obtain C true, and we'd like to exploit again the new proof of this C true. But this interpretation sounds more natural because eventually you will have to build a derivation tree that looks like this hourglass. At any point during this proof of construction, you are moving from both ends, moving downward and moving upward. So at the time of exploiting this judgment, we may assume that at the other end, we are trying to move upward, and this C2 is basically the judgment on the other side, on the other hand. So suppose that we'd like to build C true, and now you have to show that you can build C true by exploiting A true, and also you can build a C true by exploiting B true. So whichever is the case, you can always build a proof of C true build. So this is the elimination rule for disjunction. So disjunction elimination rule, down arrow with the label X and Y. So let's say this is X and this is Y. So it may appear like this one, this inference rule, this disjunction elimination rule, does not comply with the pattern here. When you apply elimination rule here, you obtain another down arrow. But this time, you apply this elimination rule to this down arrow, but in the conclusion, you have up arrow. And this does not comply with the pattern that we predicted here. In the upper half, this upper triangle, you have a down arrow, and then you apply elimination rule, and you still have another down arrow. This is the pattern that we expected, and this elimination rule appears like it doesn't comply with this pattern. However, in fact, it is actually the same pattern. You can imagine that you are moving downward, and you keep moving downward here, and you are moving upward. So you can imagine that the upper half takes this one, and the lower half is shown over here. And in the middle of this proof, this down arrow meets with this up arrow. And in the middle of this proof, this down arrow meets with the up arrow. So to summarize, still we can find this hourglass shape, this upper half and lower half, and upper half and lower half, and in the middle, these two arrows meet. So that's the disjunction elimination rule. And according to the inference rules we constructed so far, if we have a proof of A up arrow, then this proof is really normal proof because there is no detour in it. And it's easy to see why there is no detour. If there was a detour in it, so detour is introduction rule followed by an elimination rule. So we would have a detour introduction rule followed by an elimination rule. Now the question remains, if you have, say, see-through here, which of up arrow and down arrow should we use for this see-through? If you analyze this introduction rule, this one should be up arrow, because the introduction rule means that we are currently building. We want to build a new proof of see-through. But according to this elimination rule, we want to exploit. So for this elimination rule, this C must be annotated with down arrow. But in the inference rule, you have no inference rule that allows C up arrow, down arrow simultaneously. You only have this conversion rule, like a C down arrow can be converted to C up arrow. This is down arrow, up arrow. And above this inference rule, you would have elimination rule. And below this inference rule, you would have introduction rule. So this is elimination rule followed by introduction rule, not introduction rule followed by elimination rule. So by construction, this normal proof never contains a detour of this one, intro followed by elim. Now, let's see an application of the inference rules for this normal judgment. The application is, I'd like to show A disjunction negation A is not provable. Is not provable. But previously, we have shown that this normal proof has this completeness property. So instead of proving this one, it suffices to show that A disjunction negation A up arrow is not provable. These two statements are completely equivalent, thanks to the completeness of this normal judgment. So let's try to build a proof of this judgment. A disjunction negation A up arrow. So there are two ways because we are using constructive logic. Either disjunction introduction rule, left, or disjunction introduction rule, right. In this case, we have to show that A up arrow. But there is nothing more we can do about this derivation tree, because in general, we don't know what this proposition A is. So we cannot make further progress. So we get stuck here. So what about here? We take the right branch. So now you have to prove negation A up arrow. And in order to show this, you have to show, well, this negation A is basically A implies the bottom. So you assume a down arrow. This is the hypothesis, so it's a down arrow. And then you have to show bottom up arrow. There's nothing you can do about this one. And there is nothing you can do about this one either, because in general, nothing is known about this proposition A. So again, you get stuck. So the proof construction gets stuck in both cases, and we can conclude that A disjunction negation A up arrow is not provable. So therefore, this is not provable in our logic, which is not surprising because we are using constructive logic. In constructive logic, this one is not provable. It is provable in classical logic, and this one is called law of excluded middle. We will come back to classical logic later, and I have just missed the two remaining rules. Top introduction rule. So we wanna build top true. So you have to use up arrow. And the premise can be left empty. So this is top introduction rule, up arrow. And what about bottom elimination rule? We already have a proof of bottom true, and we'd like to exploit it. So we move downward, and then it allowed us to build any proof of C true. So we can build. So build corresponds to this up arrow. So we can build any up arrow. This is the bottom elimination rule, down arrow.